in this lecture, we'll investigate the basic postulates to mechanics. And here, considering three postulates in mechanics, which are postulate 2 and postulate 3. The first postulate has to do with state function. Second postulate has to do with trade-offs. So mention, so we have a hat, any parameter comes to trade-off. Then the top postulate has to do with the function. So there, in terms of physical electronics, what we are concerned about is the motion of particles. Atomic, still subatomic dimension, and this particle, our case, happens to be the electron. Okay. So that's what it is. Then, for us to be able to designate a portion of these particles, then we have to relate with the equation of motion, the field of study that provides sufficient information for analysis is therefore mechanics. So let's consider postulate. Just the state function. Now, this postulate states that the state of a dynamic system is completely specified by a state function. So, postulate states that state of a dynamic system is completely specified. State function. So this postulate infers the existence of an abstract state function, say psi, that contains all the information about the state of the dynamic system. Call that the state function is specified as a complex function defined by the amplitude psi and the phase phi. And this is a phasor having an amplitude and a phase. Fundamental distinction between the classical quantum mechanics we saw in this lecture is that in classical mechanics, the state of the dynamic system is completely specified by the position, that is position x, and the velocity. That is in classical mechanics. But, and now, if that's what it is, then it presumes that the position and velocity of a particle can be measured, or better still, specified simultaneously. That is, at the same instant of time. So, in other words, in classical mechanics, the position x, t, this s can be measured, specified simultaneously, each instant of time in the classical. And to put this other way, that I still commonly, the position and velocity of the particle at one instant of time are completely determined by the position and velocity of the particle at the previous instant of time. So it means that it is deterministic, largely because objects can be seen and touched in the macroscopic dimension. Okay? So if two particles are not at the same place or not moving the same velocity, they are obviously not in the same state. That's what we get from example. But in quantum mechanics, the position x and the velocity, so x, of a particle cannot be measured and specified simultaneously. Specified simultaneously. At the same instant of time. Hence, quantum mechanics does not presume that the measurement of the position of a particle will necessarily yield a particular value predictably. So, should a particle be known to be in a state psi, for instance, the most specific information on the position of the particle by measurement is that the probability of getting x1 relative to s2 will be the magnitude squared, with the ratio of magnitude squared of x1 to the magnitude squared state function of s2. Hence, the physical interpretation of the amplitude of the state function is that the mod of the state function of squared, the s, the state function, is proportional to the probability of finding particle range from x to x plus the x in any measurement of the position of the particle. So should it be established that only one particle exists in the spatial range, say from x equal to 0 to x equal to n, for instance, now the probability distribution function, probability distribution function, say PDF, be the same as the mod squared of the state function integrated over the spatial range of 0 to m for x equal to 0 to m. The x will give us, okay, that is integral, okay, s to m, complete this times x, which is the same as the squared. The x is the same as well. So note that if the wave function is normalized, the absolute value of the probability of finding the particle in the range from x to x plus the x will be the same as the mod of the mod squared state function dx. So hence, the expected value, expected or average value, say x rather, expected value of the position, expected position, therefore given is equal to m x x, which is the same 0 to x 8 x. Therefore, the mean square deviation is x squared from the average of the probable position of the particle. Therefore, this x is expected value squared x, which is the same as the expected squared sine x. Now, this gives the measure of the spread of the probability distribution function. X squared of the position around the average value. Okay, and then the uncertainty, which is the standard deviation, x in the position x of the particle when it is in the state psi of x is therefore given as tan x being the same as the square root square deviation. So it can therefore be inferred that the interpretation of the state of a dynamic system in quantum mechanics is probabilistic and not necessarily deterministic. Okay? Also know that the state function satisfies the principle of superposition, okay, which implies that the linear combination of two state functions, that is, say a sub 1 alpha a sub 2 alpha 2, is also a state function, where a sub 1, a sub 2 are complex numbers. In postulate 2, how to deal with equators, it states that all physically observed properties of dynamic system are represented by dynamic variables that are linear variables. So mathematically, the operator only has meaning when it operates on the state function. So in other words, the operator changes from one state to another, such that if, say, the operator Q acts on the state function, say we get a new state. Here we have two corollaries. Now, corollary 1 says that all the dynamics of the dynamic variables and corresponding readers presenting any property the system have the same functional dependence coming from variables. Presenting position so still as a first. So for instance, the operators representing the kinetic energy and angular momentum, potential energy, and the Hamiltonian therefore give us squared, which we showed earlier. So now the angular momentum symptoms. Then potential energy. Then the Hamiltonian, which has in the sum the kinetic energy operator and potential energy. Corollary 2 follows directly. So that in the Schrodinger representation, the operator, same thing, position, coordinates. Say x hat, y, c hat, or the vector, or the ordinary physical units, x, y, z. Conversely, the operators, same thing, Cartesian components, which is mental, x direction, z direction, mental, and the differential operators, like we played with previously, that is the x hat, the same as minus j, h cross, ddx, y hat, so j, h cross, dy, pz hat, so j, h cross, d, dz. And the p part may be replaced by j, h cross, d. So since the physical interpretation of the operator is that in the atomic or subatomic world, the process of measuring the property, say A, which is acting on the state function when the system is in the state psi, generally changes it into another state, say phi. This is the state function. Now, the Heisenberg certainty principle therefore follows directly. According to the classical mechanics, the dynamic properties of any system depends on the position and velocity. Hence, position and the linear momentum. So in classical mechanics, the position x and the linear momentum p, so x, in the same direction can be specified. Okay, same direction can be specified with respect to x simultaneously. Let's not forget. So that is, it is possible to measure one of the two properties without influencing the outcome of the measurement of the other property. That is, in the order of measurement of the two properties, regardless of the ordering, we should get the same outcome. That is, s hat, p sub x hat is the same as p sub s hat, s hat, such that in classical mechanics, p x hat, a hat minus p hat x hat should be equal to 0. So that when the commutator of the two operators is the same as 0, then the two operators are said to commute, meaning x hat and its position and the momentum commute in classical mechanics. Because the commutator is the same as 0. Okay, hence, since the commutator is equal to 0 in classical mechanics, means that the position and the momentum can be specified simultaneously in the same direction. Okay, so know that the difference of the two operators applied in different order is referred to as the commutator. Okay, so this is the commutator because we are ordering the two operators in different order. Okay, so for instance, if A hat, B hat minus B hat, A hat is the same as the quantum bracket of A, B, okay? Then, when the commutator of the two operators is not equal to 0, or some third parameter, that is A hat, is not equal to 0, say, it's not equal to 0, say A, quantum bracket of A hat, B hat, say is equal to C hat, then A and B are said to be conjugate variables. Then A hat, B hat are said to be conjugate variables. Okay. Commutator is not 0. And then it becomes impossible to specify the two properties in the same direction sometimes. Okay. Which is true based on our postulate 2, such that if A hat is the same as position, and then B hat is the same as the momentum operator, then we can say from the Schrodinger representation, X hat, that Px hat, X hat, operating on the state function be the same as minus J H cross dx x sine x, where minus J H cross d dx is the same as the momentum. same as the momentum operator, P hat of x. Right? Now, by the product rule, we can investigate this. Okay? Because now, product rule for us to solve for this, then if u is the same as x and v is the same psi of x, right? That's x. So d dx this, then u dv plus v du. Therefore, we use that this whole process here, same as j h cross x d dx sin x plus j cross sin x. This one the same as minus j h cross x dx sin x minus j h cross sin x. Therefore, see that s of s hat written state function same as minus j h cross x dx sin x is j h cross sin x. If this crosses this, then we have s of s hat x dot x into minus j h, that's minus j h cross ddx, which is the item operator, minus j h cross. Okay. So, in this regard, I can therefore say that this now is the same way as writing x is now x, and this is the position momentum x hat minus j h cross. Right? So it means that p x hat is the same as x hat minus j. And from here, see that if we rearrange this, p hat sub x hat minus s hat p s hat is equal to minus j h cross. And if we multiply through by the negative sign, then that this becomes positive, this becomes negative, such that s hat p s hat minus p s hat s hat is equal to j h cross. Therefore, the commutator is implies that commutator S hat E S hat is equal to J cross, right? So therefore, the commutator S hat is equal to bracket S hat is the same as S hat S hat minus other these operators or variables in different order. That is the data, right? So S naught is equal to change comes. And this is not equal to 0. So hence they don't conform. Okay, now that we have established this, so you see that the commutator position momentum, that position of momentum, theta is a non-zero value, that is, they don't convert. Okay, so, cross, which is a non-zero value, they don't commute. So according to Schwarz inequality, for any arbitrary state, say psi, the system is in, the product of the uncertainties, in any two operators is always equal to or greater than equal to 1/2 of the magnitude of the expectation value of the commutator. Which is the same, is greater than half the expected value whatsoever with respect to the state function. Okay. So even when the two operators don't convert, their uncertainty product in that particular state may be equal to 0. If the expectation value of the corresponding commutator in that particular state is 0. Okay. So for instance, the uncertainty product of the position and momentum is always non-zero value. Okay, because by Schwarz inequality, then uncertainty product between the position and the momentum should be greater than or equal to magnitude of the average value, that is half of the magnitude of the average value. Okay, cross. So hence, uncertainty product x direction greater than cross over 2 I cross over 2 c direction cross over 2. Now this engenders a statement of the Heisenberg certainty, certainty, such that since the position and momentum don't commute, they are non-zero value, then it means that the position and the momentum cannot be specified simultaneously in the same direction. So Heisenberg certainty. So for states that it is not possible to know or to specify position, the linear momentum in the same direction particle simultaneously. Meaning, the more one knows about one of the two, the less one knows about it. Okay? One knows about two, less. So, the two interpretations of the Heisenberg's certainty principle therefore follows that product of the uncertainties in the result of measurement of the position and momentum of the particles in the ensemble must be greater than or equal to h cross for 2, that is a reduced sum of 2. And that the measurement of the position and the momentum of the particle are not independent of each other, meaning they depend on each other. Hence, intuitively, the electron does not have a position and a conjugate momentum simultaneously because it is not a point particle as inferred in its classical sense. So the Bohr's assumption about the atom may not hold precisely equal mass. So you will also recall that an operator operating on an arbitrary state function will change it to another state function. Say A, at a state function will change it into another state function. But a unique set of characteristic states or state functions that will not change when operated upon by the operator are called the Eigen Functions. Okay? So, Eigen Functions are set characteristic state function change. And the Eigenvalue, value is a characteristic number, corresponding to each eigen. So, for instance, if A has traits, say psi A k, such that A sub k is the same psi A k for all values of k being the same as 1, 2, 3, 4, okay, gives the effect of an operator A hat on its Eigen function, psi k, corresponding to its eigenvalue. So for continuous eigenvalues, we have that A hat psi A the same as A psi B, where A, in this case, A is a continuous variable. Now, should the system be the eigenstate, say it is in the eigenstate system, eigenstate, say psi k, then the expected value psi A with respect to psi ak be the same psi A, which is important. And this is corresponding to the uncertainty beta A squared, which is the same as integral squared ak to A hat is expected A hat with respect to psi ak squared times psi k. And the interpretation that derives from the eigenvalue function is such that if the system is in a particular eigenstate of an operator, then any subsequent measurement of corresponding property will always yield a value, okay, equal to the eigenvalue corresponding to that particular eigenstate. No certainty, zero certainty. So, postulate Now, this postulate states that all state functions satisfy the time dependent Schrodinger equation. This J cross D T psi H cross H hat psi, where H hat is the Hamiltonian. The system is total energy. So the Hamiltonian is the operator corresponding to the total energy of the system. Okay, where H hat is the same as total energy, so this is the same. And the solution of the Schrodinger equation for the time-dependent Schrodinger equation describes completely the state of the dynamic system at all times once the initial condition has been established at t0 and the Hamiltonian. So the time-dependent Schrodinger equation can therefore be rewritten as J cross dt R C just switch cross so square square and solving by separation of variables, then the general solution to this differential equation is the same. So t sum k ck sum k t which is k ck k sum k where psi k is the Eigen function. The Eigen function of the two of a solution of the time-independent Schrodinger equation given by chart psi k sum k sum. And now phi ek of t satisfies the equation J cross phi k t t k So know that all the state functions satisfies the time-dependent Schrodinger equation. Okay? While only the Eigen functions of the Hamiltonian satisfies the time-independent equation. Okay? Now, the solution to this expression, so let's set it again. J cross. So the solution to this differential equation follows directly from these concepts. And so after the solution, general solution, k of t be the same as the exponential value is j, and I still have case k, j, so j, k, t, for the initial condition at t, okay, such that phi ek 0, that 0, which is 1. Hence, the time dependence of the solution of the time independent Schrodinger equation therefore follows directly psi k t, which is equal to psi k minus j k t equals. Okay, so now this is our first equation, this is our second equation. So at time t being the same as 0, the system is in a particular eigenstate of the Hamiltonian corresponding to a sub k. So that is t 0 sub k of t, because this expression just 0 and this 0 is 1, so everything here is to state function. And then the probability distribution function, magnitude squared, state function, that's e sub k t 0, it is e sub k, be the same as magnitude e sub k squared. Okay, and from our second equation, t equals 0. So therefore, the eigenstate of the Hamiltonian is called a stationary state of the system. Now, if the system is initially in superposition state, say psi r t 0 is equal to say m psi a psi. And at time t other than t equal to 0, the state function will therefore become t other than 0 psi t psi j t cross n psi j t. Now, the probability density function f, say, 2 squared, state function, we now same as n psi squared psi. Okay, psi j n t. Note that the probability density function contains time-varying terms oscillating at an angular frequency n equal to n e n cross, and is therefore not stationary. It's not stationary. Okay, it's 0 to stationary. Why so? Because it's negative, right? So negative j n cross j cross 0. So t. So that will be n minus e n cross c j. Right? So it's the n. So understanding the structure and the characteristics of all matter is profoundly affected by the fact that the eigenstates of the Hamiltonian are stationary states of the system. So any material stable structure must match a stationary state. And the lowest energy eigenstate of the related Hamiltonian, since it's a constant throughout time. So in theory, the solution of the associated time-independent Schrodinger equations can be used to understand and explain the structure and properties of atoms, molecules, solids, and any other steady-state forms of matter. So in summary, for any arbitrary initial state function, say psi r vector t 0 of a conservative system, corresponding time-dependent Schrodinger equation can always be solved if the initial state function can be expanded as a superposition of the Eigen functions of the Hamiltonian. That is psi 0 initial state function is the same as the sum of n c. So in this case, psi r to t at arbitrary time t is immediately known. T same psi t c j where c sub n is a constant, which is independent of time. I think this is a good place to stop, and hope to see you in our next class.